Thank you for professors introduced. I'm glad to have the opportunity to share my research results in this conference. And the definition of rare disease is different between countries. And in Taiwan, the rare disease is defined as the prevalence rate greater than 1 in 10,000 people. However, in Western countries, the rare disease is defined as the prevalence rate less than 5 to 7 in 10,000 people. And according to the statistic results, there are more than 7,000 rare diseases worldwide, affecting nearly 350 million people. And in EU and the USA, about 7% of the population is affected by at least one rare disease. And amongst the 7,000 rare diseases, only about 400 rare diseases have therapies. Therefore, about 35% of the rare disease people dies in the first year of life. So that it is important to research the rare disease. And about 80% of rare diseases are genetic in the origin. So we can use the genetic technology to perform the genotyping. In 1950s, the researchers can only use the karyotyping technology to perform the genotyping. In 1990s, the researchers can use microsatellite marker to perform genotyping. And after human genome project finished, now we can use high-density single array or next generation sequencing like whole genome sequencing or whole exome sequencing to detect the disease-causing mutations. The resolution is getting better and better. However, besides the resolution, the price is an important issue to promote the sequence as a diagnostic tool. In 2015, the sequence cost is decreased to $1,000 per human genome. So it is a good time to promote the NGS as a diagnostic tool. In 2015, the UK announced a precision medicine program, the Genomic England. They prepare to sequence 10,000 human genomes. However, they only sequenced 87,000 human genomes until now. They focus on the rare disease and the cancers. In Taiwan, the NHRI obtained a government project, Flagship programs of precision medicine. The NHRI integrates with hospitals and the university, also the companies, to study the rare disease and the 3-generation cohort to set up a genetic information system for digital health care. And in this program, a sub-program is using the whole genome sequence to diagnose the rare disease. In this program, we established the Taiwan Rare Disease Network and the participants, including the NHRI and the Taiwan Human Genetic Society that represent the scientific group, and the Taiwan Foundation for Rare Disease, Rare Disorders represent the patient groups. Our test selection criteria, including 4 criteria, involved in 1, genetic, 2, severe, 3, undiagnosed, and academic research purpose. And the Taiwan Rare Disease Network operation, including patient recruitment, next generation sequencing, bioinformatic analysis, interpretation, clinical management, and social support. First, the doctor submits a genetic diagnostic request to the TRDN, and then we will review it. If the sample, if the case has the filter, the case selection filter, we will announce the doctor to recruit the patient to the hospital. And the sample will transfer to the NHRI to isolate the DNA and perform the whole genome sequencing. Then the data will pass through the bioinformatic code to perform the bioinformatic analysis, including alignment, variant coding, annotation. And the data will send to the scientist to perform the interpretation. Then the final reports will discuss with the doctor to help the patient clinical management, and the patient may get the social support. Until now, there are 207 families pass the selection criteria, including neurodeficiency, epilepsy, SCA, hearing impairment, and residual-like patients, autoinflammation disease patients, and general undiagnosed disease. We received the samples from 124 families, and we sequenced and analyzed 86 families. Among them, the 50 families, we identified the disease casing mutations. The diagnostic rate is about 58%. This slide shows the analysis workflow. First, the sequencing rates will exclude the low quality rates, all the show rates, and map to the human genome. And the mapping criteria involved: first, we only allow the unique hit rates, and the mapping length is more than the 90% of the rates. Also, the mapping similarity is more than 90% of mapped base. After mapping, we call the variants and select the variants located in the regulatory region or the non-synonymous variations. Then we fill out the common variants that has been reported in the DBSNP or Taiwan Biomedical database. We also predict the effects of the variant on the protein function by Swift websites. In this workflow, we also detect the structural variants, including translocation, large indel, and copy number changes. To identify the candidate variants for validations, we based on the decision provided by the doctor. If the doctor cannot determine the disease, then we can use the phenotype to select the candidate genes. We also, based on the report in the PRIMA database, to select the candidate variants. By compared to the variants from the sequencing results, we can select candidate variants. We also pass to filter. One is according to the inheritance model information, and the OMI or public database. And here we will use two cases to present our study results. The case one is 1 year boy. His phenotype including the T cell, B cell immunodeficiency, and the hyper-IgE syndrome. And the patient's parents do not the same phenotypes. And this slide shows the patient's antibody distribution. Here we can see that the patient's IgM and IgG concentration is under the normal range. And the IgE's concentration is more than the normal range. The next slide shows the T cell distributions. The data indicate that the CD8 positive T cell population is smaller than the normal range, so that the ratio of CD4 to CD8 is higher than the normal range. To identify the disease casing variants, we sequenced the patient and his parents' DNA and compared to the immunodeficiency candidate genes. We discovered a homologous mutation in the ZAP-70 genes. These variations has been reported in the DBC. However, its frequency is quite low. And these variations do not link to any known disease. ZAP-70 genes has been reported to involve in CD4 and CD8 positive selection. Loss of ZAP-70 will result in CD8 positive T cell differentiation failure. And whether the ZAP-70 D521 residue is important in ZAP-70, we performed a 3D structure analysis, and we found that the D521 residue is located in the kinase domain active sites. It will form the hydrogen bond with the residue 459 and 460. And if the amino acid is changed from D to N, it will disrupt the hydrogen bonds, so that the data indicates that the D521 residues is important to involved in the ZAP-70 functions. And whether the mutations affected the T cell differentiations. To answer the question, we use CD3, CD20, and the RAM antibody to treatment the T cells and observe the casing flow in the T cells. Here's the results. The ZAP-70 D521 wild-type T cells, after stimulation, the T cell, the casing concentration in the T cell will increase, and the T cell carried with the heterozygous mutation, the T cell also increased the casing concentration in the T cell. However, the T cell carried the homologous mutations. The casing concentration in the T cell will not change like the control with on-chip. So the data indicates that the ZAP-70 D521 change may disrupt the T cell differentiation like the patient's phenotype. And the case 2. The case 2 is a boy with medical resistant epilepsy. He and his brother has the same phenotype, and their parents do not show the same phenotype. The phenotype including onset age at 2 years old, is early onset, and resistant for multiple drug treatments. To identify the disease casing variants, we sequence patients and their parents' DNA, and we find that we total identify 656 variants in those 2 patients. Among them, only 8 variants located in the candidate genes, and only 1 variant has all filters. The variant is located in SLC6A1, and SLC6A1 is the GABA transporter that is important to maintain normal neural function. And SLC6A1 is associated with autosomal dominant epilepsy. This variant is located in the C coding region 1081 regions, and will result in the amino changes from purine to serine. And the SLC6A1 P361 is located in the extracellular domain. That is important for SLC6A1 functions. And this residue is highly conserved between species, so that the mutation in this region may disrupt the SLC6A1 functions. And because their parents do not have the same phenotypes, and in this family, they have, and in these families, there are 2 patients occurs the same phenotypes. So we analyze the whole genome sequence data and find that the patient's mother is maybe is a carrier with a very low frequency mutation allele. The frequency is only 15%. And the data was confirmed by the single sequencing. That here is the results. The red color is represented to the T allele. So the allele is smaller than the 20%. So the mother is a carrier with a very low frequency somatic mosaic mutations. And whether the whole genome sequencing data can improve the patient's management, we reviewed the patient drug use history. The patient had been used 3 kinds of drug, and resistant for those 3 drugs. And because those 3 drugs do not respond to, do not target to the SLC6A1, so maybe those patients resistant to those drugs is not in the correct target. So if we use the drug that target to GAT1, which is encoded by SLC6A1, maybe the patient will respond to this drug treatment. And we discuss this result to the doctor. She will change the drug to this drug. And based on the TRDN studies, we have demonstrated that the whole genome sequence is useful to discover the disease associated variants, so that we make the molecular diagnosis possible and can decrease less treatments and improve the disease management. Also identify the potential surgeons. And we may improve the prenatal genetic counseling and functional genomic studies, also drug discovery. Finally, I will thank the TRDN contributors, including those 10 hospitals and the NHRI-ToMMo team and Yang University Genome Center, also Taiwan Human Genetics Society, Taiwan Foundation for Rare Disease Holders, and the National Center for High Performance Computing. Thank you.